Hello Earth, welcome to episode 44 of season 2 of Making Cell, a series of videos where I record myself designing and implementing a programming environment called Cell. If you're just tuning in for the first time, I recommend you go check out github.com/autocodenl/cell. I will place the link in the description. So yesterday we were basically taking a metaphorical bubble bath and just cleaning up the code, annotating it. So we're going to continue that today because bubble baths feel good and I think are actually quite necessary. So yeah, I'm being a bit of a shit shoes, but I really want to annotate these 90 lines of code we have here, which I kind of understand, but I'm pretty sure we can clean up a bit more. And then we can actually go forward with whatever it is we will go forward. I think this will be a short episode because I have to do stuff tonight besides this, unfortunately. Well, not unfortunately, it's just what it is. So let's just start with the definition of cell do, because yesterday we finished annotating cell.respond. Now define cell do, the function in charge of two things: giving the result of a call to a sequence, and two, it's like performing the expansion in result. I'm going to put this equal. Here I'm going to put colon of the call to a sequence. A call, not the call, because a call to a sequence is too non-specific. Style matters. As for the arguments, pop can be either define, right? Define or execute. Yeah. I put the quotes, sure. Malon diabolico. So it's gonna be it has been a long day, so I'm gonna be singing. I have a less self-control than usual, if you can believe that. Definition path is the path where is it? Yeah, where the sequence is defined, which we'll use to get its definition, which is really its value. Let's just use bullets, since this is already dense enough as is. Context path is the context path, always. Messages present only for the case when execute is sorry, op Malon op is execute. It is the message sent in the call to the sequence. So sorry, I'm just thinking out of turn here, but really a call to something that is not a sequence is a reference. Well, actually, a call can be three things. A call to a sequence, a call to a conditional, which is not a sequence, although it could point to a sequence, and then it could be a call to a reference, to something that is neither a sequence or a conditional. We call this a reference, right? Yeah. A way to say this, another way to say this, is that sequence or a conditional are special forms of reference. Yep. Yeah. And there are calls. Yeah. Okay, and the rest I'm not going to talk about get and put. We already had enough of them, and we'll probably refactor that into a more global way of accessing them. Yeah, wow. Una mente sana. So we start by getting the definition to the sequence. Note we pass the context path. If the definition is empty, return an error. When cell actually works, it will be so exciting to be able to get errors, clear errors that don't break the system, just tell you what's wrong so you can change it. Errors as values. I can't wait. I mean, this is so long, it's taking like so many months to get there that of course it dampens a bit my enthusiasm, but when I recover side of the whole, yeah, it's incredibly exciting. And then we get the name of the single, actually let's define. We expect that definition, that every definition of a sequence has a single text step between do and the list of steps of the sequence. For example, do message name we get the name, if it's not text, we return an error. better than name. A textual. And this is still running, working. Yes. If I do that, then it breaks. I love these errors. Apologies for the background noise. Oh, this is a good one. We forbid sec to be the name of the message. We already are going to use sec to show the expansion of each step of the sequence. And we want to avoid overwriting it. That's a good one. We forbid that there should be multiple names. And then we say of a sequence has to start a list that starts at element 1, basically. We also check that the sequence has only continuous consecutive steps. If any of these conditions is violated, we return an error. Okay. Yeah, we tested all of this, so that's how I know it works. Okay, we are at the definition. Not bad. If we are just defining the sequence, we return a single path that has 2 steps: the message name and the number of steps in the sequence. I really like this convention. I really like it. If we are here, we are executing a sequence. We start by defining output to be a single path with a single step, an empty text. If we are executing a sequence, we need to do two things. We need to compute the expansion of this execution, and we need to return a value for its response. We are not going to do this at once, but by steps. This is not unlike the way that cell.respond gradually expands paths that have multiple calls. Ascendiendo a los cielos. Why am I stripping the definition here? Oh, because it removes the rename. Yeah, I get it. Length. We're gonna use it twice, so we will define it. We'll just do it here. And we could just call it sequence length because it's a bit more explicit. I'll be right back. All right, let's continue. So we start by stripping the message name from the definition. We really need this stuff here, right? Yeah. What did I do? I'm trying to reorder the code to see if it's reasonably expressed. I think we need to explain what we're gonna do here, right? Yeah. I'm amazed at how quickly this happened a couple of episodes ago. Once we had a clear idea, we just wrote it and it worked. I'm laughing because expansion. We don't use current value at all, right? Interesting. We don't use it. Wow. Yeah, we don't use it because we do it outside on cell.respond. Yeah, nice. Okay, so we get the current expansion and we compare it for the current message, right? Yeah, we just get the current message really, which we use to compare things. And then if we update it, beautiful. And here, just compare the stuff. Okay, I understand it. Now I have to explain it. Good. I'll never have to do this again. This constant running, this constant saving. It will just be all the time happening in one place when we're running cell. When we're running cell, it will all be there. Oh, constantly running. And it will be right there. It's quite beautiful when you think about it. So I was just pondering what I just said. Yeah, we're gonna put the stripper here on top. But we need to explain the plan here. Here's the this is a tricky part. Bit tricky to understand. Let's explain it as clearly as possible. Cell do when executing, cell do needs to be check that how do I explain this algorithm? And how long do I have? 7 minutes. So when we're executing it, so I need to take to approach this iteratively. So it's like message name steps each in turn. Put them or update them. It's like idempotent essentially what we're doing. Yeah. How do I explain it? Just a minute. Sorry, I'm back. So what we want is we have already decided that the value, the final value response to the execution will be returned in output. We have also decided that any changes to the expansion will be performed not by returning those, but rather by calling cell put straight up. Directly instead of straight up. And I have a few more minutes. All right. If we think of our requirements for a cell do execution, they are the following. Put the message in colon using the message name and the actual is it a single path we get? We need to try with multiple paths. I'm not sure if we're really getting that. I don't think we are. Or are we? No, we're not. Do we support multiple? I don't think paths in the message in an execution. I don't think so. Guess we're just seeing them one at a time. That's not good. See, sometimes you find things when you're annotating the code. So we put the message in colon using the message name and the actual value of it. Take the steps in the definition and expand them one at a time. If one of them returns responds with a path that starts with stop or error, we stop and don't go further. The value of the last. Take the value of the last step of the sequence and return that as output. There are two more things that make this even trickier. We must wait until any recursive calls adds to the right in our message or our steps have results, the definition can be updated. So we need to ensure that we are using the latest one. No wonder it took me 10 episodes to figure this out. It was tricky, alright. Supla macabro. So let's go with the stripper, right? How are we going to tackle all of this? It took a while to figure out. Here it is. We consider the message to be a sort of step 0 for the definition. Basically, we treat it like a step. We write a function stripper that compares compares the existing step, takes the message or a step of the sequence and removes everything that's either an expansion or a response from it. This allows us to compare whether two sets of paths and decide whether the definition used is updated or stale. We run each of the steps starting with the message. Baby, en la noche. Through the stripper and compare them to the definition. If they change, we replace them and stop. If they differ, the one if one is different, we replace it with the one from the definition and stop. A later call will proceed with the work. Otherwise, we carry on. If we make it all the way to the end, we have a response, so we return output. When we stop, we return that empty output we defined above. Let's define stripper. For a change, we have implemented this function quite efficiently. Because responses equal and expansions are before its definition, its calls. We can look ahead to see if there's a path that has the same prefix and an at, and if so, we just filter out the path with equal or colon. Note we don't filter out paths with equal or colon that don't have those keys from coming from calls. You might have literal colons or equals. I probably need a test for that, right? Yeah, I do. All right, you can do it. I believe in you. We track the index of the first equal or colon. If there's none, we don't ignore this path. We look ahead to find a path with a similar prefix plus an at. But I didn't do the at. Interesting. It still work? Interesting, it didn't work. Why? In that case, comparing actually, let's just do this. But this is wrong, I have to fix this. Path slice. Yeah, I'm basically getting. Right, this is correct. Yeah, it is correct. But why am I using path index? This is completely wrong. It's it's first equal or colon. What were you thinking? Right? Yeah. Let's now try to do it correct. Okay, still works. Yeah, now this is exactly what it should be. I don't know why it worked. I guess it was so few paths that it just did what it should, just by sheer looking at or not. Yeah, yeah, but it was wrong. That's why we need tests. Stay in school, kids. Yeah, we're gonna have to write tests, and the more I dread it, the more I need it. Time is it? Almost there. Oh no, don't tell me that the video froze again. I'm gonna stop the video and start it. At least I realized it. Alright. Yeah. So we have this. We fixed this. Let's just comment it now. Note that we only look for paths after path index. That is, this is, we just look ahead. When comparing against the look ahead path, we slice the prefix plus 1, which should be the at, and compare it to our own prefix plus the colon, or equal, actually equal or colon replaced with no, concatenated with at. If there's no look ahead call, we return this path. Otherwise, we don't, and therefore filter it out. Good. This closes the outer loop and the function. And that's all she wrote. Yeah. What time is it? Almost. Yeah, we're gonna stop here. Thank you for watching. I'll see you next episode.